Now let's go through the assignment that we have for support vector machines. Again, this is on the same data set. This is on the same donors choose data set, and most of the tasks will be exactly what we did with k nearest neighbor or naive Bayes or logistic regression. Very similar tasks on the same data set. Of course, there will be some subtle changes as far as SVM is concerned. We also will learn how to use PCA in this assignment. Okay, we'll go through step by step, right? So the first four are basically our feature set. We have been seeing this, right? Set one is all categorical numerical features, your title represented as bag of words, and your essay represented as bag of words. So we have been seeing this. Set 2, all categorical numerical features, TF-IDF. Set 3, all features, all the text features with average word to vex. Again, set 4. So these are 4 sets of features that you have, right? Number 1. Next, so what we want you to use when you're solving this SVM assignment is to use SGD classifier with hinge loss. Right? In scikit-learn, there are 2 ways you can get a linear SVM. Right? There are 2 ways of getting it. One way is to use, let me open it. Okay, is to use your SVC, the support vector classifier. Right? Here, if you say the default kernel here is RBF kernel, but if you want, you can get a linear kernel here, right? You can easily get a linear kernel if you don't want. So if you just say kernel equals to linear, you'll get a linear kernel, right? But the problem we noticed was when students, especially students who have smaller amounts of RAM or weaker CPUs, not very computationally good CPUs, when students were running this SVC classifier, it is taking too much time for them to run our assignment. So we said, okay, if you have, so that's why we are saying it's okay not to use it. There is an alternative if you want to use a linear SVM. That is basically your SGD classifier, right? You have an SGD classifier, and if you mention loss equals to hinge, as we have seen for SVMs, what is SVM? SVM is basically trying to minimize hinge loss. So if you are using SGD classifier with loss equals to hinge, what you get is basically a linear SVM, right? So that's what we want to do, is because this is much, much faster. But the catch here is using this function, you can only compute a linear SVM. You can't get a RBF kernel SVM using this. If you want to do an RBF kernel SVM, you will have to go back and use SVC, because here it will let you have any kernel that you want. So the assignment that we have, I just want to make this clear. We will not use an RBF kernel here. We will just use the simple linear kernel. This is primarily to accommodate those students who may not have sufficient computational resources. In the real world, you might have to use the SVM, SVC and request for a larger, more computationally beefier box, right? So it's okay because some students don't have those good computers or high capability computers. It's okay. Let's just use SGD classifier with hinge loss, which is equal to a linear SVM for this assignment, so that you can do the assignments faster, right? Next, the hyperparameter that you have, which is alpha, try the hyperparameters in this range, in 10 power minus 4 to 10 power 4. Okay, and also check out your L1 regularizer and L2 regularizer also, because you can easily give that, right? So try to perform the hyperparameter tuning as we have seen, which maximizes the AUC. Use k-fold cross-validation or simple cross-validation, either your grid search, random search, or write your own stuff. The hyperparameter that we want you to play with is alpha, with both L1 and L2 regularizers. Okay, so try it out. And as usual, just like in our previous assignments, we have these plots. This is the plot of as the hyperparameter changes, how does the AUC change? Once you build the best model, how does the train and test AUCs look like? Your confusion matrix. Till here, there is a lot of code that you can reuse. We wanted to introduce a new concept to you in this assignment, right? So we will have a set 5 of features. If you notice, this has all of your categorical. Look at this. All categorical and numerical features are as is. Nothing changes. For the text features in the essay text, so let's use only the essay text. Let's ignore the title. Take the TF-IDF vectorization of essay text. Okay, you'll get a large vector, right? So take each of these is basically one project. Just use the TF-IDF vectorizer. This is basically the features here are the TF-IDF vectorizers vectorization of the essay text. Take this, right? Now, since this dimensionality is very large, can I somehow reduce this dimensionality? Can I somehow reduce this dimensionality using techniques like PCA? Using techniques like PCA, can I reduce this dimensionality, right? And instead of using all these tens of thousands of features in my TF-IDF, can I use a much smaller set of features through dimensionality reduction? And for this dimensionality reduction, we suggest you use this function called truncated SVD. We will learn what SVD is when we learn matrix factorization chapter. But just remember for now, the truncated SVD is very similar to PCA with some differences. So don't worry about it. I'll explain you the truncated SVD function here, right? The truncated SVD function works like this. You can say how many components you want. Components basically means, suppose if your initial data is D dimension, if you're trying to project the data into D dash dimension, the number of components is nothing but your D dash, right? That's what it is. So what we want you to figure out is, given that a TF-IDF vectorizer, let's assume a TF-IDF vectorizer of essay text is D dimensions, we want you to find the best D dash dimensions using the truncated SVD function. We are suggesting you to use this because this is faster. Okay, there are some advantages of using this instead of the simple PCA. Okay, so please use this function. If you want, we give you the link here. If you just click on this truncated SVD, it will take you the function definition. So please use truncated SVD to go from D dimensional space of the TF-IDF vectorizer of essay text to D dash dimensions. But the question here is, what should D dash be? Should it be 2, 3, 4? What should it be? For that, we already know the elbow method, right? We know the elbow method that we learned in PCA. Okay, what is the best number of dimensions that we need, right? So what do? You basically say, if my dimensionality is 2, 3, 4, 5, so on and so forth. On the y-axis, you plot the amount of variance that is preserved, right? Right. So as you keep going, so the amount of variance preserved will be very low if the dimensionality is low, and it will keep increasing. Right? So please use the elbow method that we learned in PCA, that we learned in KNN, right? To determine what is the best number of components, right? Now, once you get it, so because you have rest of the features, you only don't have text data here. So text data, the TF-IDF vectorized essay text, let's assume is D dimensions. We will find the best D dash dimensions using the elbow method, and we will use just these D dash dimensions of features, right? So now you have all of the categorical and numerical features. The text data is represented using D dash dimensions instead of the D dimensions, but we'll only limit ourselves to the essay text. We will ignore the title text, right? And now on top of this, we'll apply our support vector machine and repeat our hyperparameter tuning in step 2 and step 3. This repetition is not at all hard because you're just reusing the same code, right? So here, the reason we have this twist here is because we want you to learn how to use dimensionality reduction as one possible method. When you have very high dimensional data, can you reduce the dimensions and use if you have D dimensions where D is very large, can you reduce the dimensions using PCA or truncated SVD and use this dimensional data into your model? Of course, there are some pros and cons with it, obviously. Right? There are some issues with it, but let's learn to do it first, because this is something that you would be doing a lot in the real world, right? So that is important. Okay. Now, as usual, you have your whole summarization of results that we have seen in the past. So nothing new there. Again, we have given you code snippets which you can fill in with all summary, everything. So again, you can just fill in these cells so that it's easy for us to evaluate and also give you feedback.